Welcome to Closer to Truth. I am speaking with Paul Davies about his terrific new book, What's Eating the Universe and Other Cosmic Questions. Paul is director of Beyond, the Center for Fundamental Concepts in Science at Arizona State University. He is a theoretical physicist, cosmologist, astrobiologist, and best-selling science author. He has published about 30 books and hundreds of research papers across a broad range of scientific fields, including quantum gravity, early universe cosmology, the nature of time, astrobiology, and an evolutionary theory of cancer. Among his many awards are the 1995 Templeton Prize and the Faraday Prize from the Royal Society. Paul is one of Closer to Truth's top contributors. You can watch Paul's 60 videos and 24 TV episodes at closertotruth.com and Closer to Truth's YouTube channel. Paul, it's terrific to see you again. Congratulations on the book, What's Eating the Universe? It's a grand tour of our deepest science questions. Tell me a little bit about the book, and then we're going to go into it chapter by chapter.
Well, I like to describe this book as a romp across the cosmic frontier. And it's all those questions about life, the universe, and everything that you've wondered about but perhaps been afraid to ask. Well, I hope the answers are here.
Paul, let's now go through the book, What Ate the Universe and Other Cosmic Questions. Let's do it chapter by chapter. I'm going to list the name of the chapter, which is very descriptive, and just give me a very, very quick summary and any idea that hits you. I want to give the flavor for this incredibly great read. Number one, Journey from the Edge of Time.
Yes. Well, I think everybody knows that the universe began with a Big Bang, and the big issue that we face was that the ultimate origin of all physical things, including time itself, was that the start of time, or was there something before it? And so the journey really starts with the Big Bang and then goes forward and looks at all the various cosmic mysteries, but then delves back into whether there was anything there before it.
2, the search for the key to the universe. What's that key?
We've been talking a lot about the remarkable ability that human beings have to uncover the deep mathematical order in the universe, that you would never guess that beneath the surface phenomena of everyday life there are harmonious and beautiful mathematical relationships that encrypt the laws we see around us. And so you need to work very hard to get these out. But once you do it, then it really is the key to understanding everything that's going on about us. So that is the modern scientific method. It really began with Galileo and Newton, who developed, or one might say stumbled across, the mathematics that suddenly makes everything fall into place. When I say everything, at that particular time, it was the motion of planets and comets and so on. It all is beautifully explained by a set of mathematical relationships. And so that was the beginning of this unlocking the secrets of nature with a mathematical key.
Number 3, why is it dark at night? Which sounds like a childish question and actually became one of the first mysteries of the universe that was actually solved.
Yes. With the benefit of hindsight, we can see that the modern conception of an expanding universe and even a Big Bang could have been deduced a long time before the astronomers got in on the game, for the simple reason that if the universe is infinite in spatial extent, and if there are stars everywhere glowing, then on the face of it, there should be no dark parts in the night sky. The entire sky should be like a furnace and Earth fried to a crisp. And that was deduced fairly early on by a number of astronomers a couple of hundred years ago, that there was something a bit paradoxical about the fact that the sky is dark. Now, most people might think, well, of course it's dark, the sun isn't there, but the sun is only one star among what might be an infinite number. And it's true that most stars are very far away. But then the farther away you go, the greater the number of stars there are. And when you just sit down and do the mathematics, these two effects compensate. And so you're led to the conclusion that if the universe is infinite and there are stars everywhere, then the sky should be ablaze with light. And of course it's not. And that tells us really that there is a limit, there's a cutoff. Indeed, there is. There is a certain distance beyond which we cannot see, even in principle, having to do with the finite speed of light and the finite age of the universe. And that could have been put together probably in the middle of the 19th century, but it took another 70 years or so before the modern conception of the expanding universe and the Big Bang.
Number 4 is the Big Bang. We've talked a bit about before, but what insight do you have to kind of color it?
Yes. Unfortunately, this is where television can be greatly misleading. That when the Big Bang is depicted, it's usually the explosion of a lump of something in a pre-existing void, with bits being flung out, and often these fragments are compared with the galaxies sort of rushing apart. And then people want to say, well, where is the center of the universe, or where is the edge of the universe, and are we somewhere near the center? If everything's rushing away from us, surely we're at the center. And this is a gross misconception of the nature of the expanding universe, which is really better thought of as the stretching or swelling of space, that every day there's more and more space that appears around our Milky Way galaxy, around all the other galaxies. And I think somewhere in the book I actually talk about how many gallons or liters or whatever of new space arise every day, and so there is, as far as we can tell, no center and no edge, and this Big Bang really just represents the start of this process. It's not an explosion at a particular location, anything of that sort.
Most people, when they think about the Big Bang, give all the credit to Edward Hubble, because he showed that the galaxies that we thought might be part of the Milky Way are actually separate galaxies. But that was based on the redshift, which you have mentioned. And the redshift actually was developed by someone else who I was not that familiar with until I read the book. So let's give a little credit to this other guy, I think a fellow Arizonian.
Yes, well, and so I feel a sort of duty to this astronomer whose name was Vesto Slipher, because this is a local story for me. So I'm at Arizona State University in Phoenix, and then up to the north is the town of Flagstaff, and it was there at the end of the 19th century that a rich businessman, Percival Lowell, built an observatory. He wasn't interested in cosmology. He was interested in aliens, in Martians. He thought that Mars was inhabited, that the Martians had built canals, and he wanted to map these canals. He did. He produced elaborate maps showing straight lines on the Martian surface. These were all figments of his imagination, but that was the primary purpose of building that observatory. But meanwhile, more conventional astronomy was being done, and Vesto Slipher was interested in a problem at the time. So this was like the early part of the 20th century. Big debate about the Milky Way. Was that everything there is, and with just empty space outside? And what about those funny patches of light that have been catalogued by astronomers over many years? Were these like clouds of gas within the Milky Way? Or were they, as some people suggested, whole other Milky Ways in their own right, other galaxies as we would now call them, way outside the confines of our own Milky Way? And so how was that going to be resolved? Well, Slipher studied the quality of the light coming from these fuzzy patches using a spectroscope, so that's something that splits light into its colors. And what he found was that the fainter of these fuzzy patches were somewhat redder than the brighter ones. And if fainter means farther away, it implies that the more distant galaxies, as we would now call them, are systematically redder. And the explanation for that redness, now called the redshift, was very much at hand at the time, because it was known that if a light source is flying away from us at high speed, the light is shifted towards the red end of the spectrum. That's simply because red light waves are longer than blue light waves, and if something's flying away, it stretches those waves out. And so that redshift was interpreted to mean speed of recession, and therefore a simple interpretation, which was Edwin Hubble's contribution, was to take Slipher's observations and then prove from his own use of the more powerful Mount Wilson 100-inch telescope that these fuzzy patches were indeed other galaxies. He could see individual stars in them, was able to measure their distance, and came up with a sort of rough proportionality that if you're twice as far away, you're receding twice as fast, often called Hubble's law. And curiously, this was first announced not in a scientific journal, but in the New York Times in the mid-1920s. And now, of course, we tend to associate the expanding universe with Hubble's name, even though Slipher did the pioneering observations. And we even have a Hubble Space Telescope to celebrate this. We don't have a Slipher telescope. So I think he's the unsung hero of this story. It's really the birth of modern cosmology, and yet there was no fanfare at the time. No news reports. It was his observations were buried in an obscure bulletin of the observatory. But with the benefit of hindsight, we see that's really where modern cosmology began.
There is what you might call a cottage industry of Big Bang deniers, including some who are well trained in science. We at Closer to Truth get lots of unsolicited papers and documents proving this or that in quantum physics or cosmology and consciousness and other things. I'm sure you do too. But some of them, have some seriousness to it. What do you say to the Big Bang deniers? Some who might say that instead of that the redshift is related to what they call tired light redshift in a non-expanding universe. How can you show that the expansion of the wavelengths to get to red is a representation of expansion as opposed to some other phenomena which has brought that about, such as tired light?
Yes, the tired light is a tired hypothesis. You can just, of course, say, well, light gets weaker with time, but you see, then you have to break several other laws of physics. It's not just a matter of we can look at that light in isolation. There are all sorts of other ways in which we relate light to the other forces of nature. And you can't just put it in for the benefit of denying the Big Bang and not follow through with these other consequences. So mostly when you look at the specific details of these tired light theories, it just doesn't work out. And so I've never been a fan of them because I never have a problem with the notion of the expanding universe anyway. It just seems to me that this is it's part and parcel of what we understand with modern gravitation. There are many aspects of space-time that seem weird at first sight. We know, for example, that space can shudder and vibrate. These are gravitational waves. We can detect that. It can be twisted and buckled. We see that with things like binary neutron stars. So we see space, its elastic properties all the time. And so if it can be bent and can shudder, then it can expand as well. And so that really isn't a problem. And to try to sort of do away with that whole set of ideas, which are so fruitful, explain so many things, just by invoking a modification of what light does, I think is very poor science. I have to say, by the way, that the Big Bang deniers, there was, of course, a very famous Big Bang denier, Fred Hoyle, the British cosmologist, and he also had a great influence on my career, not only from his ideas, but he gave me my first job in Cambridge in 1970 as a postdoc alongside Stephen Hawking and Martin Rees and Brandon Carter and other luminaries. These were just, my fellow postdocs and young lecturers at the Institute of Theoretical Astronomy in Cambridge. But Fred didn't deny the expansion of the universe, so he wasn't proposing tired light. It's just he thought that the universe was eternal, that as it expanded, new matter was continually created to fill up the gaps. It's called the steady state theory of the universe. And it it was very hard to reconcile the steady state theory with the cosmic microwave background radiation, the fading afterglow of the Big Bang. And so by the time I went to Cambridge in 1970, Fred was already fighting a rearguard, somewhat heroic rearguard action. And it was he who coined the term Big Bang. It was a term of derision. This was during a radio broadcast in the 1950s. And he dismissed it, saying, some astronomers think the universe just began with a Big Bang, as if it's self-evidently absurd. So he was a very influential Big Bang denier, but he didn't deny the expansion of the universe. There's no way he could get away with that, I think.
Chapter 5, where is the center of the universe?
Well, a lot of people think that the Big Bang took place at some particular location in space and all the bits went flying upwards. Well, as I explained earlier, there's no evidence for any center or any edge. And the best way of thinking of the expanding universe is the swelling or stretching of the space between the galaxies. So all the galaxies move apart from all the others, roughly speaking, when you average it out. And so there is no center.
You have this incredible statistic in that chapter that you say every day space is growing larger. We can agree, but then you put a number on it, and the number you have is 100 billion cubic light years of additional space appears within the observable universe. That just seems just hard to comprehend.
Well, of course, the universe is very big, and although every day we don't notice it's a little bit bigger, it all adds up to a lot when you take into account that huge volume of space. And so it was a fun statistic to work that out. You don't often see that in cosmology books, actually working out how much extra space is per day.
I also liked your comment in that chapter where when observing the cosmic microwave background, in essence, we're witnessing the birth of the universe at every single point in the sky.
Yes. Again, people find this very hard to understand. They think, well, there was a flash and a bang, and that light spreads out as if it might from a nuclear explosion or something, and it would sweep past you and then head off behind you. It isn't like that. It comes from every direction of the sky. It's more like being in an oven, a microwave oven, in fact, because it's microwave wavelengths, and it's all around us. And any given microwave photon we can trace back in a particular direction and think, well, it's coming from that part of the sky. But the sky all around us has that temperature about just under 3 degrees above absolute zero. So there is no center, no edge. It's everywhere. You're seeing the Big Bang everywhere.
Chapter 6, why the cosmos is actually fairly simple.
Yes, the astonishing thing is, I can remember this myself as a teenager, thinking, well, this universe stuff is really interesting, but surely it's incomprehensibly complicated. There'd be no way you could understand it. And then I found a little book written by the cosmologist Dennis Sciama called The Unity of the Universe. And in it, he wrote down the equations of the universe. And these were equations I could understand, even with my schoolboy mathematics. I thought, well, how can you capture the majesty, magnificence, and the complexity of the universe in just a handful of schoolboy equations? Sure enough, you can. And part of the reason for this is that although most things around us are really complicated, the Earth, for example, is a really complicated system we don't fully understand, that when you get to the largest scale of size and the largest scales of time and average things out, it's actually pretty simple. And what adds to that simplicity is if you go back in time closer and closer to the Big Bang, everything gets hotter and hotter. We were just talking about the heat radiation bathing the universe. Well, because of this, the expanding universe, that radiation is cooling all the time, the redshift effect. But conversely, if you go back in time, it was hotter in the past. And if you go back to the first few 100,000 years after the Big Bang, it was so hot that even normal matter was broken down into a sort of plasma. And everything simplifies out. I give the example of an incinerator. You throw things into an incinerator and it's all sort of broken down to its basic constituents. Same thing with the universe. As you go back towards the beginning, it's It's very basic, very simple, and captured by a handful of equations that represent physics as very well understood. Things like the laws of thermodynamics and the laws of gravitation. It's all there in just a handful of equations. I still find that truly amazing. It's why we can teach cosmology. It would be too hard otherwise. But you can write down these equations, the students get it, they can solve the equations, actually. It's not that difficult to solve those equations and follow the trajectory of the universe. It's amazing.
Chapter 7, what is the speed of space?
Oh, yes. So this was my sort of quirky little take on the idea that motion is relative. So historically, there was always this tussle between, on the one hand, Newton, who thought of space as some sort of substance, ethereal type of substance that didn't seem to exert any drag or friction on the Earth as it went around the Sun, but nevertheless, there was sort of something there. And the alternative view of people like Leibniz that all motion is relative, and that this was an argument that went on and continues to go on in a limited way right up to our present time. That is space something that is a thing, or is it just is it relationships between physical bodies that are the only meaningful thing? But if you stop to think about it, if space is a substance, just like a fish swimming through the sea is substance. It makes sense to think about, well, what is the speed of that? And so people did worry about this. If space is going through us all the time, usually it's the other way around. People say the Earth's going through space, but it's the same thing. Imagine that space is sliding through you. You don't notice it, but you can ask how fast. And that question was asked in the 19th century, and experiments were done with light in the hope of measuring that speed, and it was found that the speed seemed to be zero, and Einstein explained all that in terms of the theory of relativity, that uniform speed through space cannot be measured. But there's still a question mark over rotation and acceleration, and whether we should think of space as a substance in relation to those, or whether we can have all motion, including rotation, as being relative. That's still debated.
Chapter 8, what is the shape of space?
Yes, so the shape of space refers to really the shape of the universe as a whole. Einstein in 1917 came up with the idea that maybe space is closed into a finite volume, a bit like the surface of the Earth. That's people used to worry if the Earth doesn't go on forever, well, you might get to the edge and drop off. At least that's the folklore. But of course, we know that the Earth is round and the surface of the Earth is finite, but there's no boundary or edge anywhere. There's no center of the surface of the Earth. So that two-dimensional surface of a sphere is an example of a space which is finite but has no boundary or edge. And Einstein thought the same was true in 3 dimensions of the volume of the universe, that you could go off in any direction, just like you sail in any direction and go around the Earth and come back from the other direction. So you could go off in any direction in space and wrap around and come back again. And it may be that the geometry of the universe is like that. We don't know. If it is closed into that finite volume, it's certainly a volume very much bigger than the volume of the universe we can see today. So it's an open question as to what the ultimate shape of space might be. But within Einstein's general theory of relativity, you can have a number of options because space is curved, and you can have a number of different topologies, as we call it.
Chapter 9, explaining the cosmic big fix, the way you like to quote Fred Hoyle, a put-up job.
Yes. Well, one of the significant things in the early part of my career is that there were a number of features about the Big Bang which looked incredibly contrived. And one of these that's quite easy to understand is the size of the bang. Why wasn't it bigger or smaller? Well, if it had been only a little bit smaller, the universe would have collapsed to a big crunch long before now. And if it was just a little bit bigger, the pieces, so to speak, would have been flung apart so much that no galaxies or stars would ever form. And it was known to astronomers that the actual rate of expansion of the universe is matched to extraordinary precision to the gravitating power of the universe, because that's what determines how big a bang you need to escape the self-gravity of the universe. And that looked like an extraordinary fix. And so along came something called the inflationary theory of the universe that explained that fix in terms of a huge pulse of anti-gravity that seized the universe in the first split second and caused it to expand faster and faster and faster. It sort of stretched it out by an enormous factor. And when you do the mathematics of that, and I have to tell you, the equations are simple. It's very easy to solve them. This is high score mathematics. You find that at the end of that inflationary phase, the universe ends up expanding at precisely this matched or big fix condition. So that's one way. Another aspect of the big fix, easy to explain, the universe looks the same in different directions. I look over there, or I look over there. It's the same temperature, the same density of matter, expanding at the same rate, and so on. This inflation theory explains that big fix as well, and a number of other features. So that's the explanation of choice today.
Chapter 10, most of our universe is missing. I assume that's dark matter.
Right, yes. So only about 4% of the content of the universe is the stuff that you and me and the stars are made from. And that's because ordinary atoms only represent a tiny fraction of the matter that's there. There's a lot of so-called dark matter. We don't know what it is. We're hot on the trail. These quite likely going to be subatomic particles which interact only very weakly with ordinary matter, pass right through us, and would represent about 25% of the mass of the universe. And then the rest is something called, referred to as dark energy, which seems to be the mass or the energy of empty space itself. And that's a whole other story.
And that other story is chapter 11. What is dark energy? You have a statistic in the book, another one, which I really focused on and enjoyed. And you say that in 1 billion cubic kilometers of empty space contains the mass energy equivalent of 7 micrograms. That's 7 millionths of a gram of mass energy, which is so incredibly small.
It is incredibly small, but the universe is incredibly big, so it all adds up to a lot. It adds up to enough to rival the gravitating power of the universe.
To see how that works really gives you an understanding of the size of the universe with that small amount of mass energy creating its gravity within 1 billion cubic light years is just astounding.
It is, and for most of my career, astronomers had no idea that this dark energy existed, and it's only in the last 20 years or so that it's become part of standard cosmology. And it does act like an anti-gravity. It's the energy of empty space itself, and it anti-gravitates. It has the effect of, one nice way of expressing it is that empty space is self-repulsive. It just pushes
and this empty space, you say 1 billion cubic kilometers of empty space, and only 7 micrograms in that, but that is now, as space grows, it's becoming more and more significant, and therefore accelerating the expansion of the universe, which was the great discovery at the end of the 1990s, 1998, I think, that really changed our whole conception of cosmology.
If you believe the observations, and they do seem to be very good, then yes, the universe is expanding faster and faster. It's now in the grip of this anti-gravity, which is now dominating over the positive pulling effect of all the galaxies and the dark matter in the universe. So the dark energy dominates all. And it's sort of weird because it is just the energy of empty space, and people think, well, why should empty space have energy at all? And my simple answer is, well, why not? There's no reason why not. But actually, there's a particular reason why it should, having to do with quantum physics and the quantum vacuum, which bestows an energy even upon space which is totally devoid of any other particles. We know it's there. We can actually measure the energy in the lab. We can measure um, often called vacuum energy. It's not the dark energy we've been talking about. It's related to it, but it does lead to measurable effects. So we're pretty confident that quantum physics of the vacuum does have an energy associated with it. It's just we can't work out exactly how much.
Chapter 12, where does matter come from?
Yes, so one of the great mysteries of cosmology, still unexplained, is that when you make matter in the lab, for example, in a particle accelerator, you're colliding, for example, protons at high speed, as in the Large Hadron Collider, you make a whole shower of particles, but you also make antiparticles. And the antiparticles are like the mirror images of particles. So the archetypal one is the electron, has a negative charge and a particular mass. Its antiparticle, often called the positron or anti-electron, has a positive charge and the same mass. And this was predicted way back in the early 1930s. And it's true, every particle that exists has an antiparticle. And when you make matter in the lab, you always make antimatter to go with it. Yet in the universe as a whole, we see only matter and almost no antimatter. So how did the Big Bang go bang and cough out just matter? What happened to all the antimatter? Well, we have a sort of rough and ready explanation that in the beginning there was matter and there was antimatter, but a slight lopsidedness in the concentration with slight excess of matter. And all the antimatter annihilated against most of the matter, because if a particle and antiparticle come together, they disappear in a flash of radiation. So the idea is they're all annihilated, and the radiation they produce is precisely that background heat radiation, the fading afterglow in the cosmic microwave background. And the matter that we're all made of is just the residue of non-annihilated primordial matter that was formed in the Big Bang. And so that's the essence of the theory. Very hard to actually get the numbers right, though.
Chapter 13, gravity conquers all.
Yes, so this is the story of how stars become overwhelmed by the force of gravity and collapse to form black holes. And it's an idea that was first introduced quite a long time ago and was met with disbelief right up until my career. And now they're an established part of astronomy.
Chapter 14 continues from that, warp time and black holes.
The black holes are the ultimate in time warps. That Einstein's general theory of relativity says gravity slows time, and the gravity near the surface of a black hole is so intense that time literally stands still with respect to our own time.
And that's an amazing concept because if you're there, and of course that's physically impossible, but imagining you would not sense any difference in time in your world. But as we look upon it as observers to that world, it looks like it's frozen. But if you were there, it would just seem normal.
Yes, as we say, time is relative. It would be normal to you as you plunged into the black hole. And of course, you couldn't come out again because you'd be beyond the end of time as far as the universe is concerned.
Chapter 15, is time travel possible?
Yes, so this is a fun topic. I think most of my colleagues would say no, but I've always toyed with the idea that traveling into the past is not totally ruled out. And if it turns out it is impossible, then it tells us something very profound about the nature of the laws of physics.
Chapter 16, what is the source of time's puzzling arrow only going forward?
I did my PhD thesis on this topic, and so it's dear to my heart. I think we all recognize that there's a distinction between past and future, very fundamental, this arrow of time. It's usually related to thermodynamics, the fact that the entropy or disorder of the universe is going up all the time, and so it must have been more ordered in the past. So we trace back the source of this arrow to the Big Bang itself, and the fact that the universe was born in a state of almost perfect order. And that's one of the great mysteries that is left unexplained.
Chapter 17, the black hole paradox.
So Stephen Hawking showed in 1974, mathematically showed, that black holes are not perfectly black, but glow with heat radiation, often called Hawking radiation. And as a result of the energy they lose, they shrink and get smaller and smaller and eventually disappear completely. And so the problem is what happened to all the stuff that fell into the black hole in the first place? Does it just sort of vanish from the universe? And that was the prevailing view at the time, and still is in some quarters. But Hawking arrived at his conclusion about black holes by applying quantum physics. And the laws of quantum physics say that information should never be destroyed, that any information about what falls into the black hole should still exist somewhere in the universe. And so that's called the black hole paradox. It's still unresolved. There's something of an industry of theoretical physicists working to figure out, is the information destroyed, or if it comes back out into the universe in the Hawking radiation, how does it actually get out? It's one of the unsolved problems. I hope young people watching us now will feel motivated to come into theoretical physics and have a crack at trying to solve that one.
Chapter 18, A Theory of Everything. You have a great sentence in that chapter. You say the graviton is far and away meaning your favorite particle, because no one has ever detected one.
That's right. So the history of physics is really the history of unification, matter and energy, and then electricity and magnetism and the other forces. And there seems to be this momentum towards converging on a final unified mathematical scheme that you might wear on your T-shirt, for example. And we're not there yet. And so there's a lot of effort at attempting this unification. But the unification involves not just the particles of matter, but the other particles that convey the fundamental forces. The graviton is the one that conveys the gravitational force, and gravity is so weak that nobody's ever detected a graviton. But it had better be there, otherwise the whole edifice of theoretical physics won't make sense.
Chapter 19, Fossils from the Cosmic Dawn. And in this, you address one of the most breathtaking aspects of cosmology when I first learned about it, and that is assuming inflation to be the case, where the universe vastly doubled in size within 10 to the minus 36th or whatever it is seconds, and multiple times, so that it expanded enormously during that period. What would have happened is that the quantum fluctuations in that very, very small area would become the seeds of the galaxies today, because there'd be these minute differences in mass energy density, and those would then gradually increase over time to become galaxies. That's such a breathtaking concept, and you yourself, with your former student, were involved in helping to provide the theoretical foundation for that. So give us a sense of that.
Well, the amazing thing is that we embarked on this work before the inflationary theory became popular. And the reason that we looked at this problem is because my student, Tim Bunch, needed to get his PhD, and therefore had to give him a problem that looked like it could be solved, equations that could be solved. And we wanted to look at quantum effects in an expanding universe. But the way that inflation works is that the universe doubles in size in a fixed period of time. It doesn't matter what that period is. It's the same basic concept. So it's what we call exponential expansion. And it turns out that in an exponentially expanding spacetime, you can solve the problems of quantum physics, of quantum field theory, exactly. You can write down exact solutions. And so this, my student was able to do. And we could ask questions like, well, what would the fluctuations, quantum uncertainty, lead to fluctuations in energy in the vacuum state in this exponentially expanding universe? What would they be like? And we worked all that out and published it, and it never occurred to me that anybody would ever make use of that. But within a very few years, when the inflationary explanation for the Big Bang became very popular, this what became dignified with the term the Bunch-Davies vacuum was already there and was able to provide an explanation for the ripples in the cosmic background heat radiation. You look at this afterglow of the Big Bang, and it's not precisely uniform. There's a few parts in a million variations across the sky. These variations are very nicely predicted by this Bunch-Davies vacuum. And so that's been the explanation of choice actually for really quite some decades now. So I'm very proud of the work that Tim did, and proud of the fact I've played a hand in explaining something without which we would not exist. If it wasn't for those very tiny variations in the density of the universe back at the end of the inflationary phase, then galaxies would never have formed. No galaxies, no stars, no planets, no people to wonder about it. So our very existence depends on these quantum fluctuations from this first split second of the universe, writ large and frozen in the sky. We can actually see or detect those fluctuations directly, and they're huge in scale. Everything's inflated up. But ultimately, these are quantum fluctuations from that first split second.
Yeah, that is really remarkable. I remember when I first heard that, I mean, it literally took my breath away. Chapter 20, this also takes one's breath away. Can the universe come from nothing? A favorite topic of Closer to Truth?
Yes. Well, people often ask the question, well, what happened before the Big Bang? And when I was a student, the answer was simply nothing, on the basis that there was no space and no time before the Big Bang. It was the origin of space and time itself. So some people have interpreted that to mean, well, we don't, that the universe can burst into existence and it's completely explained because it comes from nothing. But of course, it's not literally nothing. You need laws of physics for something like this to occur. And again, we usually appeal to quantum mechanics. So if you believe there's just one universe that erupts into existence in this manner, it would be a quantum process. And the laws of quantum mechanics have to somehow exist. They have to transcend the universe, those laws and the laws of gravitation and other laws too. So if you believe that the universe, that the Big Bang was the ultimate origin of all physical things, you have no choice. You have to believe that there are laws, fundamental mathematical laws that transcend the universe that can then explain how that universe came to exist. And we're back to the Tower of Turtles, and where do those laws come from and how do we explain those? The pendulum has now swung. So a lot of cosmologists now don't think the Big Bang was the ultimate origin of all physical things. They think it was just one bang among many, that we live in a vast assemblage of bubble universes that overall is eternal. Any given universe like ours might have a beginning, a life cycle, and an end, but the entire assemblage is everlasting. That may change. It may be that in another generation the pendulum will swing back and people will think, no, just one universe.
You pose it as kind of a dyadic choice, either that these unexplained laws of quantum physics, etc., are already out there in some, I don't know, platonic sense or outside the physical existence and account for how the physical cosmos lawfully appeared spontaneously from nothing, as we've defined nothing. Or the alternative is that the laws and the universe together, as you put it, burst forth ready-made, a joint package, to quote you, a joint package of marvels with no explanation whatsoever.
That's right. And so I mentioned earlier about how my colleagues want to follow the chain of explanation back to the laws of physics and then say, oh, not going beyond that. But it really does mean that as you've explained it, you have this choice, this dichotomy, and very few of my colleagues want to face up to that.
Chapter 21, how many universes are there? And you begin wonderfully by, you say, you doubt that it's 153, which means
Right.
you doubt it's a specific number. It has to be either 1, 2, which is interesting, or infinite.
Yes, I think that's right. Yeah. So you think why two? Well, I talked about electron and the antiparticle, the positron. They're formed in pairs, or maybe universes are formed in pairs. So there might be two. But above that, it would be bizarre. I think if there was some specific number. So it looks like an infinite number. And as I just mentioned, the favorite idea now, the multiverse theory, is that there's not just one Big Bang, but an infinite number of bangs scattered throughout space and time, and it's going on for all eternity. So in that case, there would be an infinity of universes. So we've gone from one when I was a student to an infinite number now. But as I just said, we may, in another generation, may go back to the idea of a single universe.
Chapter 22, the Goldilocks enigma, which you have focused on throughout your career.
One of the oddities about the universe is it seems to be remarkably well suited for the emergence of life. If you change some of the laws of physics or the cosmological initial conditions just by a tiny amount, the consequences would be literally lethal. And so what is the explanation for this? Just like Goldilocks porridge, the universe seems to be just right for life or rigged in favor of life, and nobody can quite agree on why that is so, but it's clearly a profound fact about the nature of the universe.
You make the point that while some people claim that the multiverse theory solves that problem, because you have an infinite number of universes and different laws, some will be amenable to life, and if some would be, or even one would be, and it's infinite, you would have that an infinite number of times. End of problem. But you say no, because even if you have a multiverse, you still have to have the characteristics of that multiverse. How is it generated? What are the universe generating properties of the multiverse? So you're basically just kicking the problem up a level, maybe making it a little bit more general, granted, but it's still a problem.
Well, it is a problem, and a lot of my colleagues think that once you go to a multiverse, if you can have different laws, everything is solved. But the most popular version of the multiverse, which is called eternal inflation, it's like a sort of scaled up version of what we were just talking about, the inflationary scenario, that in this eternal inflation where bubble universes pop up spontaneously all the time, you still, to describe that, still have to appeal to the laws of quantum physics, the laws of gravitation, general relativity, assumed space and time, and a whole bunch of other things has to be there. So instead of having one unexplained universe, you've got one unexplained multiverse. And it's true, you get many universes out of that, and some of these will have life and some won't. But it's not a complete answer to the reason for existence. It is in a way, it's a distraction from the ultimate question.
That's a very different view, and I think a view that needs to be heard. You have one statement in this chapter, which is one of the very, very few that I sort of take some disagreement with. And you say there may be no end to this ontological paper trail. Is it no end to the paper trail? Because that sounds like turtles all the way down, or no end to our capacity to adjudicate what happens at a certain level of turtles.
Well, we discussed this a little bit earlier, and I'm not a fan of the terror of turtles, or not a fan of just saying there is a super turtle and we'll just take it for granted and get on with the job. I would like something more complete, but I also conceded that this may simply be beyond the human intellect, and it may be that even our AI descendants would struggle to make sense of it. I sometimes ask myself, is the reason that we get stuck on these really deep foundational questions because we're asking the wrong question, that we framed our notion of explanation, or what we would regard as a satisfying aha moment. Now I see how the universe is put together. We've framed it in the wrong language or in the wrong concepts. So I'm open to the idea that a future generation would simply recast all these problems in a totally different way and maybe come up with satisfying answers. But that's just a wish. We may have to concede that this will never happen.
Well, some philosophers go in that direction, but the quick answer then is brute fact. Bertrand Russell's famous comment, the universe is just there, then and that's all, and you can't say anything more about it.
Yes. Well, as I said earlier, that I think just declaring the universe exists as a brute fact is ultimately makes it absurd. There is no explanation for why the universe is as it is, and that to a scientist that seems very unsatisfying. But of course, my sense of dissatisfaction doesn't mean that that is the way it is.
The universe has no obligation to make us feel satisfied.
Right.
Chapter 23, we get to the big question. It's the book's title, What's Eating the Universe?
Right, so this is a fun topic. So we've talked about how the universe began in a state of almost perfect order, that there was a Big Bang, everything was very simple, very smooth, but there were fluctuations, quantum fluctuations that were imprinted on the universe, which gave rise to its large-scale structure. And I mentioned the Bunch-Davies vacuum, and all this accords really very well with the nature of this afterglow, the cosmic microwave background radiation. It explains all those fluctuations, but it's not a perfect fit. There are some anomalies. There's a weird asymmetry between two hemispheres, for example. But the one that really stands out, and is the title of the book, is a big patch, or it seems like a void, a low temperature region in the southern hemisphere in the constellation of Eridanus. That is anomalously cooler than the rest. It doesn't look just like a quantum fluctuation. It looks like something else has caused that. I quip that it's almost as if a cosmic giant has taken a bite out of the universe and left a super void. Now, we don't know what that is, but one possible explanation, due to Laura Messini-Houghton, is that if you believe in the multiverse and there are all these different bubbles, different big bangs and so on, then maybe occasionally these bubbles can collide. Is it possible that another universe sort of banged into ours and has left a scar? Now that's a very speculative idea, but more generally, what we're talking about is a universe that's born in almost a pristine condition, but it's got some scars and blemishes. And so is this an indication of some external effect, something from outside the universe, or is it something that's gone a bit wrong or a bit different within our universe? Or could it be that if the Big Bang wasn't the ultimate origin of all physical things, that this void is almost like a portal that will enable us to look outside of our universe, or before our universe, or beyond it, or whatever is the best way of describing that. These are very speculative ideas, but it's, seeing as this is a book about unfinished business in cosmology, an explanation for that cosmic void is high on my list of things we don't understand and we need more work.
Yeah, it's an important part of the book is to not only talk about the great successes of precision cosmology, but all the open questions as well. So this is critical. That really leads to the next chapter, chapter 24, where you ask, is the universe actually a botch job, which is the polar opposite of a put-up job?
That's right. So here we're talking about a universe that's perfect, almost, but has flaws. We've just been talking about some geometrical flaws that are possibly there. But what about the Goldilocks enigma? I said just right for life. Well, just how just is that just? Could it be that it's sort of okay? It's acceptable porridge, but it's not perfect. And so we can ask the question, could the universe have been constructed slightly differently so that there was more life? It was more congenial for producing life. And the cosmologist Fred Adams had a crack at that. He thought, well, are these laws of physics so fine-tuned that they are producing an optimal state of affairs? And he concluded, no, there could be changes that could be more favorable in terms of the emergence of life. And that sort of appeals to my sense of humor, that the universe is pretty good, but slightly botched. In my irreverent moments, I like to think that there is a God, but this God has students and he gives them projects, and this is a sort of A minus, our universe A minus. It's okay, we'll let it go because it works quite well, but try harder next time.
As an ad, we can say that Fred Adams' videos on fine-tuning and how they work are on Closer to Truth, so people can follow up. Chapter 25, Are We Alone? Which is this great question of astrobiology. And what fascinates me is that the spectrum of thought on this it couldn't be broader. From, as you put it, a complete fluke, we're the only intelligent life, maybe the only actual life in the universe, or it is almost inevitable, kind of a tropic force of the universe that drives life. So, I mean, you can't define it any broader, that range.
Right, and when I was a student, it was assumed that life on Earth was a bizarre fluke and that we would be alone in the universe. Now the fashion is to say the universe is teeming with life, but we are just as much in the dark about how life began as we were back in the 1960s. We still don't know whether it's like a sort of dream run of fluky chemical reactions that would occur only once, or whether there is some sort of deep principle, a life principle, if you like, that is embedded into the universe, into the nature of things, so that wherever conditions permit the emergence of life, sure enough, it follows. I'd love to believe that there is such a principle in the universe, but it's not there in our physics textbooks. You won't find it in chemistry textbooks. Biologists have no idea what I'm talking about. So the notion that there is a sort of inbuilt tendency for life to burst out wherever it has a possibility, that's a very wonderful romantic idea. But we have no evidence for it. And that's why I attach such enormous importance to finding life elsewhere in the universe. If we find that there's more than one genesis, and that it hasn't just spread around, more than one genesis, that life does arise against all of the raw odds throughout the universe, then this, I think, would be the most profound discovery of all time, because it would show that the universe is intrinsically life-friendly, and that we can feel at home in the universe, that we're not just the products of some freak accident, that we are inbuilt into the great scheme of things that includes life, and I would like to think mind and comprehension as part of its natural outworkings. That's what I'd love to believe, but we don't have a shred of evidence for that at the moment, in spite of the fact that so many of my colleagues declare that the universe is teeming with life. They have no right to do that without buying into this romantic package I just outlined.
I like how atheists and theists will take this question of is there life in the universe broadly or narrowly to reinforce their own perspective. Take each part of this kind of 2x2 matrix. If you're an atheist and the universe is and we're a fluke, that means we're such a that there's no God because life is so rare. The theist would take that, see that God created us in such a special way.
Yes,
and if there's broad life in the universe, and it is throughout the universe, the theist would say, see, God made the universe teeming with life and life-friendly. And the atheist would say, sure, human beings are not so special. God didn't create you. So no matter what we find, the theist and atheist will each be reconvinced in their own beliefs.
I think you've summarized that beautifully. I won't attempt to do it again.
Chapter 26, is E.T. in our backyard?
Well, this is a fun speculation recently that SETI, the Search for Extraterrestrial Intelligence, has really focused on sweeping the skies with radio telescopes, hoping to stumble across a message from an advanced civilization on the other side of the galaxy or something. But the universe is not only very big, it's very old. And there were stars and planets around long before Earth even existed. So if the universe is teeming with life, and if there's a fair amount of intelligent life, advanced civilizations, then they could have sent probes, technology of some sort into the solar system at any time during the Earth's history. And so then the question is, rather than sort of looking very far afield for evidence that we're not alone, why don't we look in our immediate cosmic neighborhood, on the moon, in the solar system, or even as Jim Benford, a physicist in California, has suggested, we look at some strange objects that are sort of following the Earth, playing tag as we go around the sun. They're co-orbital with the Earth. When I say strange, these are chunks of rock, but he thinks that would be an ideal place for some sort of alien listening post or something like that. So that's a very speculative idea, but it's a fun one that we could investigate more closely for very little cost.
Chapter 27, this is a very deep probe of reality. Why am I living now?
Yes. And so this chapter begins with what was actually the case. I used to lie awake as a child at a very early age and be baffled by the fact that I learned about all this history, the Roman Empire and so on. And I thought, well, why wasn't I living then? Or the Second World War was the backdrop to my entire life. Why had I missed this exciting episode in British history? It baffled me as to why I was living at a particular time. I never really thought, why am I not living in the far future? But one could equally ask that. And so it's a question that I think, I don't know if it troubles everybody, it's really very hard to answer on a human timescale. But on a cosmological timescale, there's a very good reason why intelligent life exists in the universe at this sort of time, a few billion years after the beginning. And that's in terms of the time it takes for carbon, the life-giving element, to form, and for there to be stars around and so on. So that we do actually have an explanation for that. But the only explanation I can find at the human level as to why I'm living in this particular century and not, say, in the far future is perhaps because there's nobody in the far future. That's a very gloomy view, often called the Doomsday Argument. But perhaps most humans who have ever lived and will ever live are sort of clustered within a few millennia around about our epoch. It's a rather depressing conclusion, which I'm not sure I actually believe.
The Doomsday Argument, which we cover on Closer to Truth, is based on the principle of mediocrity, that you shouldn't expect yourself to be on the extreme ends of any probability distribution. You should assume you're somewhere in the middle. And if you are in the middle, that means that the long tail in the future of human existence is cut off at some point. And that's the reason for your pessimism, and we would all share it. But the argument has always seemed to me to be too facile. I mean, do you really buy it?
I don't think I do. The counter to skeptics is usually, well, what makes you think you're so special? But you see, it's very ill defined, because what constitutes an observer? And occasionally I'll have arguments with people about this. There are a lot of beetles in the world. Do they count as observers? What about AIs, and what about it could be that humanity is doomed, but what about our artificial intelligence descendants? Are they observers? Or what about if there are extraterrestrial beings, could stretch into the very far future? They all count as observers. And so it depends on your definition of typicality. But this rather narrow one, that you have to be a human observer, I think is far too narrow.
Chapter 28, the fate of our universe. What are the alternatives, and what's your best guess?
So again, I hark back to when I was a student. The choices were, well, either the universe will go on expanding, or it will collapse back on itself to a big crunch. And the observation suggested it was on this tantalizing borderline between those alternatives. That's the big fix we talked about. And for a long while, those were just the choices. But then along came the discovery of dark energy and the accelerating expansion of the universe. We can throw in another one, which is that if this dark energy isn't constant, if it gets stronger and stronger, then the acceleration of the universe will get greater and greater. And there is a state of affairs where the universe will meet an end not by collapsing to a big crunch, but the opposite, by expanding at an infinite rate, often called the Big Rip. It too would represent an end or a boundary to space-time. Now, of course, we can always play games like supposing that the universe does collapse to a big crunch. Well, maybe it'll bounce, and there'll be some sort of new universe that would emerge from that. And then we have to take into account that if there isn't just one universe but an infinite number, then the fate of our own particular universe is incidental, because there will always be other universes being born, going through their life cycles. And then even the bizarre speculation that if the universes can arise as quantum fluctuations, bubbles in this bigger system. Maybe we could engineer our own bubble, make our own baby universe, and decamp to it from this one, and perpetuate this for forever and ever. So all of this stuff is, of course, extremely speculative. But the idea of that the universe will have an end, that there will be something, either end with a bang or a whimper or a rip or something, I think is a deeply fascinating one, and part of the motivation for the careful cosmological observations. It's not just to tell us how the universe began, but what its ultimate fate might be.
The penultimate chapter, 29, is in a sense the summation in a broad visionary way. And you ask, is there a meaning, that famous word, meaning, is there a meaning to it all?
Yes, and of course we've been over this in our earlier conversations, and I start that chapter with a live TV show I was once on many years ago, involving a bishop and an atheistic philosopher, and a discussion about meaning, and the philosopher getting very exasperated. This was A.J. Ayer, Freddie Ayer as he was known, and saying, but what do you mean by mean? And it was actually really rather a shallow discussion. But I think that the point is, if we want to go beyond simply cataloguing the facts of the world, and ask, well, does it make sense? What is it about? Is there something deeper going on here? Then we tend to cling to words like meaning and purpose, but as I explained earlier, maybe these are too culturally loaded terms for us to use, and that we have to find other ways of describing. But I'm totally convinced that we should not just stop at simply accepting the world as it is, making an inventory of particles and forces and declaring, well, that's it. We won't ask anymore. I think we do need
You quote Steven Weinberg's famous statement, the more the universe seems comprehensible, the more it also seems pointless. We had the opportunity to speak with Steve some years ago, and I asked him, did he still believe that? Because he had written that many years before I'd asked him. And he said, yes, he did.
That's right. I think he sort of hardened his attitude towards the end of his life. And I sort of see it the other way around, because if there isn't, I mean, the word point again, point or pointless, these are human categories, but it's the same sort of thing. It seems to me that if the universe is not about anything, if you like, if it doesn't have a point, if there isn't a coherent scheme of things, then there's no real justification for doing science, because you do science taking as an act of faith that what you will find will make sense, that as you dig deeper and deeper, you may not know what you're going to find, but you assume that you don't find absurdity. And so I think to be a scientist, you really have to assume there is a point to it all. But maybe point is not the optimal word here. It's the one Weinberg chose.
You state near the end of this marvelous book, What Ate the Universe, that the biggest of all questions is this: will science, as you're saying, will science ever advance to the point where we can fully grasp the deeper level of rational order? Now, my question to you is, are you restricting your epistemological arsenal to science alone? Could it be that the rational order escapes the methodologies of science?
You're asking a very good question. And of course, we haven't carefully defined science. What I've implied, it's a mixture of mathematical exploration and careful experimentation. But science, and in particular the laws of physics, which I've dwelt upon at such length, may not be the only way to organize facts about the world. And I'm very open to the idea that we might have another scheme, another conceptual framework that could lead us to make discoveries in other ways. Now, you may say, well, that wouldn't be science. It would be, science plus, or some other word that we would invent. But I don't think that the current scientific method is the be-all and end-all. In particular, I'm struck by the fact that the method that physicists use doesn't adapt very well to living matter, to living systems. The notion of fixed laws and specifying initial conditions and so on. It's just not a very good fit. And so maybe after 3 or 4 centuries, the notion of fixed mathematical laws and changing states has run its course, and that we need another conceptual framework. It may be that we wouldn't call that science, I don't know. But I'm open to the idea that there will be other forms of discovery. I'm not, I should say, I'm skeptical of the notion of sort of revealed truth, that I might have some amazing, internal experience and some achieve some wisdom that I couldn't get through everyday explanation or exploration, and that therefore I can explain the universe, but only in terms of some deep spiritual experience I've had. People have those experiences, but I'm not sure it's very helpful in explaining the universe to people who haven't had them. So I'm a fan of exploring the universe and coming up with explanations in a way that can be communicated to other people without saying, oh, well, if you don't know what I'm talking about, then I can't help you.
I've said that if I had that type of internal experience of suddenly understanding reality, that would be the last thing I would trust.
Yes, I think that's exactly the case. In the same way that all sorts of amazing things are revealed to me during dreams, but I don't take them very seriously in the waking life.
Chapter 30, the final one, you look to the future. What's new on the cosmic horizon?
As I mentioned, that I've lived through the golden age of cosmology, but this has left us with many unanswered questions for the next generation of scientists to get their teeth into. And so the last chapter catalogues a few of these things. Some of them are questions that we've dealt with, like what happened before the Big Bang. We don't know still, or how the universe will end. These are we don't know. The big unsolved problem among most of my colleagues is that the final unification of the forces and particles of nature is incomplete. We have partial unification. We have amazing machines like the Large Hadron Colliders made the Higgs boson, but bafflement as to what comes next. In particular, there's a concept that unifies the particles that convey the forces of nature with the particles of matter. This is a mathematical concept called supersymmetry, and it was always supposed that supersymmetry would be confirmed by the Large Hadron Collider, and it hasn't been, and nobody knows how to unify these particles any other way. So that remains an open question. And the black hole information paradox is another one that I've mentioned. The dark energy and dark matter, in particular the dark matter particles, nobody knows what they are, but the hunt is on to try to detect them and identify them. And then there's a very curious discrepancy that's arisen just in the last couple of years in the rate at which the universe is expanding. I said right at the outset that when I was a student, cosmology was a very sloppy sort of subject, not a precision subject at all. It's now already very precise, and many of the cosmological parameters have been measured to very high precision. And the rate of expansion in the universe, which goes back to Slipher and Hubble, how fast is the universe expanding? That was all over the map for quite some decades, and then it sort of settled down to a particular number. But now there's a discrepancy that's crept in. Two different methods for measuring that rate of expansion don't agree to within about 10%. And so is that going to sort of come good? Will one side give in or find errors, or will they meet in the middle? Or does it indicate that there is something fundamentally wrong with our whole cosmological model? So these are just a few of the things that my colleagues and I worry about and think would be good topics to work on in the future. And so my conclusion is that the golden age of cosmology has not yet come to an end. We're still in that period of amazing discovery, and there's still mysteries out there that have to be solved. And I hope I live long enough to see the solution for some of them at least.
It was a tremendous read. I got this great feeling of fully understanding each of these areas. We've dealt with all of them on Closer to Truth, but you've encapsulated them so well in this easy read, yet very profound. I did have one question, though, when I finished, and I asked myself, what about consciousness? Certainly, if physicalism is correct, and ontologically there's only mass, energy, and the physical laws, then consciousness means nothing in the grand sense. It means something to us personally as kind of a cosmic accident, but it means nothing, full stop. But if we should take consciousness seriously, as perhaps more and more people are doing, and I think you've mentioned it yourself, perhaps in some fundamental sense that consciousness could be a new prism to sense the spectrum of reality.
Like you, take consciousness seriously. Some of my colleagues want to just define it out of existence, but I think it's obviously, I wouldn't even say a fundamental, I'd say it's the fundamental aspect of our experience of the world, because that's the way we have access to the world. And so any truly comprehensive unified theory will not only have to explain living matter, I said earlier how difficult that was, but conscious matter or consciousness, whether it's in matter or wherever it is, we don't even know. I think it's wide open at this stage. I often say there are three great origin questions. There's the origin of the universe, the origin of life, and the origin of consciousness. And we've been talking about the origin of the universe, and we know a lot about that. I think we're in fairly good shape when studying it. The origin of life, we was hot on the trail, but I think we're still a bit stuck on that. The origin of consciousness, however, we don't even know how to correctly frame the concepts. We all sort of feel we know what it means to be conscious, but how do you embed that in a scientific paradigm? I don't know. I think we're still at step zero on that one, although I follow very carefully what my philosopher colleagues say, and a handful of scientists who dabble around in the consciousness area. I think it's deeply fascinating, but I think we...
What's Eating the Universe is a terrific book, Paul. It's a fun read. I recommend it to everyone, and everyone can watch Paul's Closer to Truth videos at closertotruth.com and Closer to Truth YouTube channel. Paul has 60 videos and 24 TV episodes that we feature. Paul, it's an absolute delight to see you again. You're in super shape. Looking forward to the future. Please come back before another billion years.
Well, I always enjoy our conversations, Robert, and thank you so much for being a gracious host and asking such perceptive questions that enable me to give free rein to my somewhat quirky imagination.
Viewers can watch Paul's 60 videos and 24 TV episodes at closertotruth.com and Closer to Truth's YouTube channel.